Okay, let's see if I can start. Okay, so the last thing we were talking about yesterday is this thing that's called like finite differences, and the idea there is the idea that there is that you want to like approximate the value of the derivative of a function at like a particular point. So here, the goal is to approximate f prime of a for a function f of x and a given point and a given and a given point a. Yeah. Okay. And let me see, where did I write this? And so, like, like the way I was doing it yesterday is that we started with Taylor's formula, right? So you can start with the Taylor formula, and like depending on how you play with the approximation, you get depending on how you use like Taylor's formula, you get different approximations. So the most basic one that I kind of like showed you was the one that's called like forward difference approximation. So the forward difference, I'll try to draw it like kind of like in a picture so that you see how it looks like. Um, in forward differences, you have the point A on the number line. Then you imagine you move an amount H. Uh, so you are at the point A plus H. Okay. In this case, for these purposes, usually when you think of h, you think about it as being like a positive number. So that's why I'm drawing a plus h to the right. Okay, and at those two values of x, right, like the function, like it has two particular values. So like maybe the function here has like a value which let's call f of a, and here maybe the function could be like has value f of a plus h. Okay. And so in the forward difference, like the idea is to approximate the derivative. You say that in forward differences, you say that the derivative is approximated by f of a plus h minus f of a divided by h. And that is more or less like, literally that is the same as like the linear approximation that you know from Calc 1. Like this is no different from that. Like, that's usually what you would have done in Calc 1. When you linearize a function, like that's more or less like the same answer that you get there. So this is kind of like it's essentially the same as like the linearization from Calc 1. Okay. And then like the thing is like the reason the thing with the big O notation, what's useful is that it's a little bit more precise, because it gives you kind of like an estimate of like how much you're failing when you do this approximation. So kind of like the correct statement, if you wanted to see it like as an equality, would be to say that f prime of a is f of a plus h minus f of a divided by h plus big O of h. And again, that means that, whatever, what that means is that whatever the difference is between these two quantities, kind of like the dominant term depends on h. So kind of like it would be something in a sense like um, h plus some other stuff, but like h is the leading term. That's how you would think of that. Um, and then like another one that I mentioned, like kind of like towards the end of uh, um, yesterday's class is this one, which is called like the central difference approximation or centered approximation. So in this, well, it's kind of like the name suggests. Now, kind of like you center the point A. So you have like A, you have A plus H, but you also kind of like it's a little bit more symmetric because then you would consider A minus H. Okay, so you have here the value f of A, you have here the value f of A plus H, and I don't know, let me draw here f of A minus H. Okay, and again, like the way we found it yesterday was like plain with Taylor's formula. And here, what you would find is that if you manipulate Taylor's formula in an appropriate way, you would find that f prime of A in this approximation, you approximate it by f of A plus H minus f of A minus H divided by 2H. Okay? And kind of and then here the idea is that again, that's kind of like the approximation that you would use if you wanted to see it kind of more like as an equality. Like the way to write it as an equality is to say that f of prime of A would be f of A plus H minus f of A minus H divided by 2H plus O of H squared. Okay, so what that means is that in this approximation, the error term, the kind of like the dominant term in the error is H squared. And that's kind of better because again, like the idea is to think of H as being very small. Okay. So if you think of H as being very small, then like like H squared is smaller than H. So kind of like the idea is that in a sense, these should converge faster to the derivative. They should give a better approximation to the derivative than the first method. Is that making sense? Now, the other thing that I was mentioning yesterday, and this how this stuff connects to some of like the stuff we have been discussing about polynomials, is that another way to think about this formula. So here's like another way to find this approximation. Like a different way to find it is that you know you have 3 points actually here because you have a minus h, a, and a plus h. So you have 3 points which are a minus h, f of a minus h, comma a, comma f of a, right? And then a plus h, comma f of a plus h. Okay, so in the notation of the first exam, this is what I think we call like x0, y0, x1, y1, and x2, y2. Okay, and when we talked about the Lagrange interpolation formula for like a polynomial, kind of like the idea was like if you have like if you had like 10 points, then you would find a polynomial 1 degree less, right? Like so if you had 10 points, you would have find a degree 9 polynomial. Here, because you have 3 points, you would find a parabola or a degree 2 polynomial. So if you use the like the Lagrange formula, you can find a parabola. So using Lagrange interpolation, you can find a degree 2 polynomial, degree 2 polynomial. through these 3 points. I think I had written it like yesterday as well. Like, I mean, it doesn't, it's not too hard to find. Like, you just find that P2 of X is like, well, let me write it this way. It's 1 over 2h squared, f of a minus h, x minus a, x minus a minus h, plus f of a, x minus a plus h, x minus a minus h, plus f of a plus h times x minus a plus h, x minus a. Okay. I mean, it's quadratic, because like you see x with x, x with x, x with x. So like it's always like a quadratic polynomial. And kind of like it's not too bad to compute. If you find the derivative of this polynomial and evaluate it at a, you literally get back this expression. So you can check. I mean, it's like a good thing to check. It's just you just have to use like the product rule. It's not too bad. So you can check that P2 prime evaluated at a gives you the gives you the formula that we obtained from Taylor's theorem with this like central approximation. Okay, so what that means is that like um, you can kind of like turn things around because like the way you could start with Taylor's formula to try to find approximations for the derivatives. But another way to approach the problem is to kind of like try to find a polynomial first. You find the derivative of that polynomial, and then you use that as an approximation for the derivative. So what it means is that so the idea is that instead of using Taylor's formula directly to approximate the derivative, to approximate you can try to find a polynomial and use p prime of a as an approximation for the derivative. Is that making sense? So just to give you an idea to turn things around, like here's another famous approximation for the first derivative, which is called the 5-point stencil. And this will show you that you kind of could keep going if you wanted, but like the 5-point stencil, here's another one, another example. Well, as the name kind of like suggests, you would use like 5 points. So here, you could think of like using a, a plus h, a plus 2h, a minus h, and a minus 2h, right? So I mean, you also can do it like symmetric, so that it's kind of like centered at a in a sense, um, and that gives you like the 5 points, right? Which are a comma f of a A plus H, f of A plus H. Then you have here A plus 2H, f of A plus 2H. Of course, it is like a longer calculation. I'm just kind of like showing you what you could do. So like let's say here's A minus H, f of A minus H, and then A minus 2H, f of A minus 2H. Okay, so you have 5 points and you could try. Okay, so as we were talking about earlier, with 5 points in the Lagrange interpolation, you find a degree less, a polynomial of degree less, 1 degree less. So 5 minus 1 is 4. So in this case, you would try to find a degree 4 polynomial. So if you use the Lagrange interpolation formula, you find a degree 4 polynomial, which is too long to write down explicitly. So I won't write it right now. But so using the Lagrange interpolation, you can find a polynomial of degree 4 passing through these 5 points. Okay. And if you were, it's like if you're willing to spend some amount of time like doing the algebra, it's like an interesting thing to work out. It's just like a little bit too tedious. But you would find this polynomial of degree 4, and you can check that if you take the derivative of that polynomial at A. Like again, like you can try to check it if you want. Then if you do that, you will find this answer. So that gives you like kind of the 5 point stencil. It's like kind of like another approximation for like the derivative, like the first derivative of the function. But no, it involves this combination. And the idea is that you could actually come up with this formula just by using Taylor's just by playing around with Taylor's approximation. Like but like it's kind of like it requires a little bit more of you know you have to be more clever because then you have to think about how do you want to play with Taylor's formula and how to combine the different uh, versions of Taylor's formula to kind of come up with this like combination. Whereas in the polynomial perspective, it's kind of a little bit more direct because it's like, okay, you choose like the points, you find the polynomial, you take the derivative, and so it becomes a little bit more mechanical. That's what I'm trying to say. So that's kind of like the advantage of the you know, of the polynomial perspective, because it's kind of like it can become a kind of like somewhat easier method to find you know, to find like these formulas for like the approximations of the derivatives. Is that making sense? Okay, so before I continue, it's a good place to do some brief discussion. So okay, let's see. So I posted earlier today. Okay, I already posted the study guide for the exam. So remember we have the exam on Monday. It's kind of like the same format, like the same setup as like the first one. So you don't have to show up to the Zoom meeting or anything. Like everything will be set up for you to take. So you can check the study guide because there I mentioned which formulas you need to memorize and which ones you don't. So you can take a look at that. There's only one thing left that I'm going to cover like in the next 30 minutes. Like I don't think I'll need well like today, but which is something like about the Chebyshev points, but that's like the only thing left. But there you can find that. And then I also uploaded some more problems on the PDF of the problems of the PDF, but I'll upload more today, and I'll also post kind of like a mock exam. I'll try to post like a mock exam today, and maybe the solutions tomorrow, so that you can take a look at it, um, to so that you can have like also like something more, like more of a like a reference. But yeah, like we're almost done. Like I just have to mention something brief about the polynomials and like this thing with the derivatives. But so you can take a look at that, and like kind of like last time, I will have like some like less like office hours on Monday morning just in case there are like last minute questions. But I'll try to see if I can finish today a bit earlier to also like answer more, like give you more time to ask me questions if you want to ask me something more specific. Okay. Is that okay? Are there any questions about that? Okay, so now that I'm here um on Firefox, I can show you something else because so the idea, okay, uh hopefully this kind of like is like what I just said, gives you like a sense of why it is convenient to use polynomials to find derivatives. Like they are related to the things that you would find using Taylor's formula. Um, like kind of like in terms of like topics left for this class, what we want to discuss is like how to approximate integral. Okay, which also will be very simple now that we have like the polynomial technology in place, and also how do you approximate solutions of differential equations. But that's kind of like similar because like to find a differential equation, you kind of like have to integrate it in some sense. Um, so kind of like those two things go hand in hand. So like the only two topics left for the course are kind of like how do you approximate integrals and how do you use the approximations for integrals to find solutions of differential equations. That's what we will do after the exam on Monday, so like starting on Tuesday. But the difference, there is somewhat of a difference between a derivative and an integral, right? Because if you think about it, like when you're trying to find a derivative, if you're trying to find the derivative at a point, you only care about what's happening near that point. Um, so like usually you say that derivatives are local because local in the sense that it only when you're trying to find a derivative, you only really care about how the graph looks of the function near that point. But when you're doing an integral, right, when you're trying to find an integral, you kind of like on a given interval, you kind of like care about the entire behavior of the function, right? So, derivatives are kind of like local, whereas integrals are global. That's kind of like the mindset to have. And so next week, when we start approximating functions with polynomials to find their derivatives, it is useful to try to use approximation schemes where like the polynomial captures more accurately the graph of the function. So like long well, not long time ago, because this course like goes pretty quickly, but a couple of weeks ago, maybe during the second week when we talk about the Lagrange polynomial, I told you a little bit about this Broughton's phenomenon. Um, so just to kind of like remind you, by the way, this animation is I posted the link on Canvas if you want to play with it because it's kind of like fun. But I have mentioned some of it before, but now I'll kind of like go into a little bit more detail. So the idea in Roy's phenomenon is that you can have like a function, like for example here, like the function is 1 over 1 plus 25x squared. And you see they're looking at the interval from -1 to 1. So the function is in blue, okay? Okay, the graph of the function is in blue, and you can try to, use a polynomial, find a polynomial that interpolates, that passes through certain points and use that as a Lagrange interpolation. So, for example, here, uh, they are choosing 5 points, which are these 5 red dots. I don't know if you can see them that easily. You choose these 5 points. And then you try to find the polynomial that passes through those 5 points, and that's the blue curve that you see there. Okay, but these are called like equally spaced points because if you look at their distance, at the difference in the x values are equally spaced. So okay, so this is called like a equally spaced grid sometimes. But like the idea in Röntgen's phenomenon is that you could increase the number of sample points. Okay, which now you see here, like now I changed from 5 to 10. So now you are sampling at 10 points. So now like again, you have 10 points and they're equally spaced between -1 to 1. That gives you 10 corresponding points on the graph. And then you find the polynomial um, passing through these 10 points. And the idea in Röntgen's phenomenon is that if actually you were to increase the number of sample points, you start getting this funny behavior kind of like towards the ends of the interval, where like the function actually starts like oscillating more wildly, okay? Which is kind of like this thing that you see here, like what's happening in blue with the function. So, and again, I'm about to explain a little bit of what's going on here in a moment. But what I'm trying to say is that, if you were trying to use like the Lagrange interpolation to kind of like approximate the graph of the function, um, then using points that are equally spaced can sometimes like run into trouble. Okay, and this is kind of like what this Röntgen phenomenon is trying to show. And oh, by the way, here in the graph below, like if you look under the graph, it gives you kind of like the error in the interpolation, and you see kind of like the error is completely almost close to zero, which means like it's like a great approximation. Like almost throughout the entire of the interval, but it kind of like breaks down towards like the end, and so that's where it kind of like it has like a big sharp peak towards the edges of the interval. Um, okay, so and again, I'll say in a moment like a little bit of why that's going on because it's actually a somewhat complicated story. But the idea is that sometimes like if you sample with points that are equally spaced, you can run into trouble. So there is another way to sample points, which are called Chebyshev points. And like hopefully Chebyshev, we already talked about that, like when we talked about Chebyshev polynomials. So they will be related to Chebyshev polynomials in a moment. That's why I also spent some time talking about them. Um, and I'll tell you how those points are found in a very soon. But the idea is these points are not equally spaced. Okay. In fact, they are kind of like more spaced. Like they become more frequent towards the edges of the interval. So if you kind of can see here, like the red dots, the idea is that the red dots tend to like accumulate towards like the edges of the endpoints. Not the endpoints. Well, yes, towards like the edges of the towards the endpoints of the interval. But kind of like the pointing that, so as you see, there are kind of like more red points towards -1 and 1 than elsewhere. But here, like the idea is that if you actually have done the sampling using Chebyshev points, then the interpolation behaves a lot better. And you can kind of like you can kind of like see here that like actually let's see. This like looks pretty fine to me. Like I don't know how this error is being measured, but oh, like well, like this error is like okay, this is really small. But the idea is like if you sample with Chebyshev points, like then like the approximation to the graph of the function is a lot better. So what I was going to do now is kind of like tell you a little bit about what these Chebyshev points are, and why somehow they work better than like when you do equally spaced points. So that's what I was going to do next. Let me go back to that. Okay, let me go back to my tablet. So again, now what we're trying to do next. So again, we're thinking now in terms of like for purposes of differentiate for integration, right? So the next step is to approximate integrals. And the idea will be that you want to approximate that integral by integrating a polynomial instead. So the idea will be in, to do the approximation, to do this approximation. You find a degree n polynomial. Do the integral of the polynomial instead. Okay, but so for that to work, we do want like a polynomial that is close to the function. Okay, so for that to work, okay. And so like before I kind of like say what we're going to do, here's like a thing you could have thought about. Like here's like a possibility you could have had. So you could have used like the Legendre polynomials, right? Because if you remember, we talked about that like I guess when like maybe late last week and or earlier this week, you know, when you have a function, right? We talked about how you can project it, right? So you could try to find like the projection, right, of this function, which if you remember, you can like that was kind of like that allows you to write like the projection was going to be kind of like the degree n polynomial that's closest to the function in a sense, right? And I had given you that this you can express as a combination of the degree n, well, of the distinct Legendre polynomials, right? So here pi of x was a Legendre polynomial of degree I. So like an option you could have, I mean, one possibility you could have tried, right? So one option would have been like, and this is option one, is that to approximate. Uh, But here, that's where you do have to, and this is kind of like the philosophy of numerical calc analysis, like where you have to actually think, okay, how realistic is this in practice? Like, as a theoretical approach, this is okay, but when you kind of like look at the details, that is kind of like problematic because to find these coefficients, if you remember, like to find the coefficient, you have to take inner products, right? So the issue with this problem, with this approach, is that to find the coefficients, if you remember, to find the coefficients, you had to find the CIs. You had to use to compute like some inner products, which were like these these integrals. So if you're telling me that you're trying to approximate the integral of the function, you shouldn't use as an your approximation approach something that itself requires you computing integrals of the function, if you know what I mean, right? Because like these, in order to compute this, like already like the degree zero like gender polynomial was just one, so already this implicitly assumes that you know how to find the integral of the function, right? So if what you're trying to do is approximate the integral of the function, you cannot have like as your part of your method something that requires it, right? So it's kind of like a little bit circular if you do it from this perspective, because it just like assumes what you wanted. Okay, so that's like the only problem that this has. I mean, it's a big problem, so I'm not trying to minimize it. Like, but from a numerical perspective, that is what's problematic about this, because it kind of like assumes what you were trying to do. Okay, so like this is like ends up being somewhat circular. Okay, so that is like the disadvantage of this method. So option two, and this is what we're actually going to be doing next week. Option two is to do the Lagrange interpolation. So option two will be the Lagrange interpolation, where the idea is that you had, let me draw the function, right? So maybe this is the graph of the function from -1 to 1. Again, everything is being worked out here from -1 to 1. So here you have the interval from -1 to 1. Okay, and the idea is that I'll choose, well, I have to choose n+1 points. Okay, so I'll call them like, oops, I'll call them x0, x1, x2, x3, up to xn. Okay, so you choose n+1 points. Those gives you that gives you corresponding points on the graph, right? So that gives you a point here, 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 and then you would try to find the Lagrange polynomial. Then you try to find the Lagrange polynomial that passes through all these points. So then you find the degree n. Well, y0 is f of x0, sorry. F of x0, x1, f of x1, up to xn f of xn. Okay, so maybe the polynomial again would look, I don't know. This could be the degree n polynomial. I don't know. Okay. Now the thing is, there's and now I'm getting, so it all boils down to how do you choose the values for the x's. So then if you are going to use this approach, the problem becomes how you should choose like x0, x1 up to xn. So the question becomes how do you choose x0, x1, x2 up to xn? Because once you have those points for the x values, that gives you the corresponding y values, because now you are sampling. That's kind of like the word that you use. Now you're taking the y values from the function itself. So now you have like the y values. And if you have like, and once you have the x and the y values, you have the points, and then you can find the polynomial, right? So it all boils down to the question of how do you choose you know, how do you choose these like values for x0, x1 up to xn. So like the most obvious option, but what I was trying to say earlier is that this not always does not always work, and that's what I'm about to explain. But kind of like the most obvious thing you could have tried probably is called like equally spaced points. So the most obvious choice is to choose the points to be equally spaced, to make the points equally spaced. And so just to kind of like draw it, like, I mean, it makes sense like if I draw it on the interval. Uh, what I mean by that is that if I choose like the interval -1 to 1, then kind of like the distance from x0 to x1 is the same as the distance from x1 to x2, which is the same as the distance from x2 to x3, which is the same as the distance from x3 to x4, up to xn. So the idea here is that the um, in absolute value, it gets like, you know, well, I mean, I'm ordering them so they're increasing, so that's not a problem. So what I'm saying is that in equally spaced points, xn minus xn minus 1 is the same as xn minus 1 minus xn minus 2, which is the same as x4 minus, well, or let's, which is the same as x3 minus x2, which is the same as x2 minus x1, which is the same as x1 minus x0. Okay, so, and you can call the common distance between the points h if you want it, just to kind of like be consistent with what we were doing before. So this common distance between the points, like the common separation, would be h. So h is a distance between a point, is a distance between the points xi between any 2 points on this grid, two consecutive points. Okay, and that, I mean, like if you never have thought about this, like this is like a perfectly natural thing to try to do. Like, it seems kind of like the most democratic way to do it, right? Like because there's no preference for which points you use, like in the sense like all they're all equally spaced. So it's kind of like um almost from a probability perspective, that's kind of what you would guess. Kind of like the issue here. No, is that this sometimes can go wrong. So, and that's kind of what I'm going to say a little bit more now. So the issue is that sometimes This can go wrong. And this is related to this Roentgen's phenomena that I was telling you, showing you earlier on the animation. So like usually that's just referred to like as Roentgen's phenomena. Okay. So the reason, again, like I will kind of like give a very brief idea of what can go wrong because this is actually a complicated story. So like it does require, like if I wanted to do like an accurate answer, it would require more information than probably what you know because like it requires more knowledge of complex numbers and other things. But kind of like the idea is that there is a formula for how much there is like an error formula by how much like if you have a function and you try to interpolate it using Lagrange by how much they differ. Okay, so the reason for what's going on or why this may not be the best strategy, this choice of points may not be ideal is that there again there's kind of like an error formula that says that for any choice of points, and that's important, that for any of points x0, x1 up to xn, the difference between the function and the polynomial that you would find, the difference between the function and the polynomial um, is given by the absolute value. Let me look at the. Uh, where did I write it? Oh yeah, yeah. It had like the n plus one factor. Oh, actually, this doesn't require the function. I'm missing. I still need another term. So what this kind of like tells you, okay, say you're trying to find you make the choice for what the x values should be. You can once you have the x values, you have the corresponding polynomial of degree n using the Lagrange interpolation. And what this formula says is that the function differs from that polynomial by something that depends on the nth plus one derivative of the function times this product of single terms. Which, if you remember, I don't know how much you remember from Lagrange because we did it a couple weeks ago, but this is how we kind of like would start the construction of the Lagrange polynomial, right? You would multiply the kind of like all the x values together, well, like x minus x0 times x minus x1, and then to construct the Lagrange polynomial, you would delete one at a time and like do all the thing. So here, like here, cx is a number on the interval -1 to 1, which may depend on x. It's actually like a consequence of the mean value theorem from Calc 1, believe it or not. So it's not too bad. This formula itself is not too bad to derive. It's just like a little bit of not worth it to do it right now, but the book does derive it if you're curious. Like you can read it in the book. What I'm trying to say is that basically this gives you like a formula for any choice of points you know, for any choice of points for the x values, how much the corresponding polynomial will differ from the function. Now, the idea is that in this case, like, you have little control over this term, like, because this involves like the nth plus one derivative of the function. So this, like, whether it's not something that you can control, like, because it depends on the function itself, right? The only thing you have under your control is how do you choose these values for x, the x0, x1, x up to xn. So this is outside your control. Let me just emphasize this. So this you don't control because I mean the function is what it is. So like its n plus one derivative will be what it is. Like that's you cannot do anything about that. So you don't control this. But you can control this because you can control that x. You can choose x0, x1 up to xn. So this is what you can control. Since you can choose. You can control this since you are the one who is allowed to choose x0 up to xn. Since you can choose. Okay, so the question all boils down to how, so the question then becomes, how do you choose the different values for this x0 up to xn that makes kind of like this quantity vary the least. So like what you want to do is like find a choice of values for the x's that give you the best control over that quantity, you see. So the question, so the choice of x0, x1 of through xn should try to kind of like make small in some sense, and that's what I'm not trying to make too precise. Should try make small how much, I mean, more like the fluctuations, like how much varies over on this interval. On the interval -1, 1. Okay. And the idea, which this is the complicated part, but the idea is that if you choose the points to be equally spaced, that doesn't give you the optimal control over this product. So the idea is that choosing equally spaced points is not the optimal solution. That's just what it ends up happening. So the idea is that the choosing equally spaced points is not optimal if you are trying to minimize this quantity. Okay. And of course, like that is where I'm saying like it's a little bit more complicated. Like, explaining why that happens is a little bit like above the capacities of this course. I did post, let me see if I can show you quickly on Canvas. For those who are curious and maybe have taken more like advanced math classes, maybe, that could be readable. So if you go to modules, if you go to modules where I have like these extra readings, I posted like a chapter that kind of like explains what's going on here. If you want to read it, you don't have to read it, but only if you're curious. And it kind of like goes into, like what happens if you make different choices for the points, et cetera, et cetera. The thing is like this is related to complex numbers, and even like you can make a relation to electrostatics. Like it is like a weird like thing. It's like an interesting topic. It's called potential theory. because you can kind of like define electrostatic potential here, like kind of like a Coulomb potential. And they're trying to minimize kind of like a configuration, like where do you put electric charges on the plane? Um, and then the idea is that, for example, if you use equally spaced points, then like the fluctuations can diverge more compared to if you use other choices of points. And so what I'm going to do next, it kind of like tell you like the choice of points that we will use, which are called these Chebyshev points. And again, we will just we will just take it as a black box, our article of faith that you should use those. I mean, it's not the only one that you could use, but they are better than the equally spaced points, and that's all that we need to know. So, but that's like the last thing that I'll explain today is kind of like what are these Chebyshev points, and then we would, once you have them, then you just, whenever you try to find a polynomial, you would just try to find a polynomial that goes through those points. Okay. Um, so I think this is a good place to maybe do the 5-minute mini break because like the only thing that's left is just me telling you what those points are, which is not too bad, but like it's a little bit different from what I have been saying. So let's just say 11:30 actually, and then at 11:30 I'll continue. And if you have anything to ask me, you can as well in the meantime. I'll pause the recording. Okay, so let me, mention this thing about the Chebyshev points, which is the last topic for the exam. So as I was saying, for whatever reason, well, I kind of tried to give you an explanation, but it is just a case of that basically equally spaced points is not that great for in certain situations, and the Chebyshev points work better. So that's what I'm going to tell you what they are right now. So what are the Chebyshev points? So the idea is that instead, if one chooses x0, x1, x2 up to xn to be the Chebyshev points, then the polynomial approximation is better. Then the polynomial. Okay, so what are these Chebyshev points? There are actually two kinds, but like I'll just I'm just going to always use these ones. So like I won't try to distinguish them, but there's kind of like Chebyshev points of the first kind, Chebyshev points of the second kind. Also, just because there's like Chebyshev polynomials of the first kind and Chebyshev polynomials of the second kind, but I always just use one of them, and that's our like Chebyshev polynomials. So if you remember the Chebyshev polynomials, they were t0 of x was 1, t1 of x was x, t2 of x was 2x squared minus 1, t3 of, like I'll just write two more, 4x cubed minus 3x, and t4 of x was 8x to the 4 minus 8x squared plus 1. Okay, so again, in terms of x, it is not super obvious where they come from, and that's where you have to kind of like use some trigonometry, because if you, again, because we're working on the interval -1 to 1, if you use the interval from -1 to 1, then you can say that x is cosine of theta, right? And then this becomes, well, cosine of 0, which is kind of silly. Then this is cosine of theta in terms of, if you replace everything in terms of theta, right? Then this is cosine of 2 theta, cosine of 3 theta, and cosine of 4 theta. Okay, so in terms of theta, which is easier to understand, the Chebyshev polynomial is just cosine of n times theta. And so, kind of like the idea, I didn't say it explicitly, but it's kind of like easy to see from this perspective because cosine is always between -1 and 1, that the polynomials themselves are always between -1 and 1. So, notice from this representation, notice that the Chebyshev polynomials are always between -1 and 1. Which is actually like interesting information. And so the Chebyshev points are just the points where the Chebyshev polynomial assumes their max and the means. So they're just the points where you know the of like the local. I mean, they will actually be absolute max, but they are like the absolute max and mean of the Chebyshev polynomials on this interval. So the Chebyshev points. So what is the Chebyshev points? Um, x0, x1 up to xn. They are the points which yield local max mean of, well, not, I mean, they're absolute max and mean, an absolute max and absolute mean of the Chebyshev polynomial of degree x. In other words, they are, because the Chebyshev polynomials are between -1 and 1, they are the points where the polynomial achieves those values. So they are the x values, they are the points where the the Chebyshev polynomial is plus or minus 1. Okay, so far so good. Is that making sense? And so where does that happen? It's super easy to find if you use this second version of the shape polynomial. So you want cosine of n theta to be plus or minus 1. When is the cosine plus or minus 1? That is at 0 and at pi, right? So n theta has to be 0 or pi, right? Um, but that, like, or multiples of that. So like the easiest way to say it is that you can say that this has to be a multiple of pi, any multiple of pi, because that includes 0 pi, 2 pi, 3 pi, 4 pi, like, they kind of like go all over the place. And so that tells you that theta has to be j pi over n. So here j goes from, and because you want, and then the corresponding values for x, which is what I care about. So here j is an integer. Here j is an integer. And so the corresponding values for x, because x is cosine of theta, would be cosine of j pi over n. Okay, so the Chebyshev points, basically there are n plus 1 Chebyshev points, which are cosine of j pi over n. So, and I could have started with that definition, and I could just have said that the Chebyshev points are those are, but it's kind of like nice to see where they come from. For j between from 0 to 1 up to n. Because that way you guarantee that the x values are between -1 and 1. So for example, let me do two cases. So let's say that what if n equals 2? So what if n equals 2? Then the Chebyshev points are cosine of j times pi over 2, and j goes from 0 to 2. Okay, so how many points does that give you? Um, it gives you, so you get cosine of 0 pi over 2, you get cosine of 1 times pi over 2, and then you get cosine of 2 times pi over 2, right? And that's cosine, cosine of 0 is 1, cosine of pi over 2 is 0, and cosine of pi is -1. So on the number line, right? On the number line, on the interval from -1 to 1, the Chebyshev points are -1, 0, and 1. Those are the three Chebyshev points. And those are the max and the mean. Okay, so those three values is where the second degree Chebyshev polynomial takes values -1 and 1. Okay, so this is where these are the points where the second degree Chebyshev polynomial takes values ±1, as you can verify very easily. Here's another one. What if n equals 4? I mean, I'm just choosing something where I can evaluate the cosine easily. There are not that many options, right? So what if n equals 4? If n equals 4, then you have to look at cosine of j times pi over 4. And here j goes from 0 to 4. So that gives you cosine of what? It gives you cosine 0 pi over 4, gives you cosine of 1 pi over 4, gives you cosine of 2 pi over 4, cosine of 3 pi over 4, and cosine of 4 pi over 4. So again, that's cosine of 0, which is 1. That's cosine of pi over 4, which is what? 1 over root of 2. That's one way to write it. This is cosine of pi over 2, which is 0. And this is cosine of what? 3 pi over 4 is minus 1 over root of 2. And this one is cosine of pi, which is -1. So these Chebyshev points on the interval -1 to 1, where are they located? They are located at -1, -1 over root of 2, 0, 1 over root of 2, and then 1. And the idea is that those 5 points are the absolute max and mean for the degree 4 Chebyshev polynomial. So these are the absolute max and mean for the 4-degree Chebyshev polynomial, which is 8x to the 4 minus 8x squared plus 1. Is that making sense? So these are the like how the Chebyshev points are like looking. Now, what's kind of like cool is to see what happens if you choose like a large n. Like, what if n had been very large? So that's what I'm about to show you. Um, but is it okay how I'm finding them? Well, okay. So actually, I did this because I was okay. I didn't have I was having issues finding like like a cute animation online. So I was going to try let me try ChatGPT to see how good of like an animation it does for me, and it actually was pretty decent. Okay. Um, so first, like if you can see my screen, I asked it, "Oh, could you do the animation that shows that?" And sometimes they're also called nodes. So can you do an animation that shows the Chef nodes? And it kind of like showed me this at first, and I'm like, "Okay, could you show me more nodes?" Because I didn't think this was too representative, right? Um, so now it shows me the Chebyshev nodes or like the Chebyshev points when you choose n equals 30. And there, like you kind of like see a little bit better what's happening because you see that the points are kind of like accumulating towards -1 and 1, right? Um, and you can even download the animations, which I like. But this is actually not what makes them interesting of the on the Chebyshev points is what if you like don't draw them only on the x-axis. You should also draw the corresponding point on the unit circle. So that's what I asked it next. If I could show me the node and the point on the unit circle, which it didn't do a good job here, but then I asked, I kind of like explained better what I meant. Oh, and then it did a very nice animation. So this is kind of like the animation that you should keep in mind. Because basically the blue points are the Chebyshev points and the red points are the corresponding points on the unit circle. Okay, so what this shows you is that the blue points kind of like accumulate, right? They accumulate towards -1 and 1 towards the end of the interval. But on the unit circle, I think this you can kind of see it. Like on the unit circle, they are kind of like at the same distance of one another. So they're equally spaced on the circle. It's just that their projections are not equally spaced, which is kind of like cool if you think about it for a second. So that's kind of like that like so in terms of the angle theta, the points are equally spaced in terms of the variable theta, in terms of like the arcs, like the arc length. There's as much arc length from one point to the next, but when you project them down, they are not equally spaced. So there are still, in a sense, equally spaced points, but not in terms of like the x variable. So the idea is that in a sense, for the Chebyshev points, the natural variable is theta. If you think about it, it makes sense because like they're like the formulas are way more simple. So in terms of the variable theta, it is actually like the equally spaced points. So it's like a cute animation because it kind of like shows you two things. First, like the points do accumulate towards uh, the edges of the interval, but from the perspective of the unit circle, they're actually equally spaced on the unit circle. Okay, so let me write that down. And let's see if I can. Let's see. But I thought it was kind of like fun to see if, to what extent like I could get like a nice animation of this fact from ChatGPT, which actually did a pretty good job. Uh, so like the two facts that I to mention here, and I'm almost done. So the first one is that then the shape when n is large, like I mean, and it happens pretty quickly as you can see, but for n large, the shape points accumulate near ±1. However, the corresponding points on the unit circle are equally spaced on the circle. Okay. However, for any n, the corresponding points of the unit circle are always equally spaced. Okay, and that brings me to the last formula that I was going to write today, which is like the Chebyshev interpolation of a function. So what is the Chebyshev interpolation of a function? So the Chebyshev interpolation of a function f of x is just a degree n polynomial that you get using Lagrange interpolation with the Chebyshev points. So this is the degree n polynomial you get using Lagrange interpolation, passing through x0 f of x0, x1 f of x1 up to xn f of xn, where x0, x1 up to xn are the Chebyshev points. Okay, and that's the most important thing. X0, x1 up to xn are the corresponding Chebyshev points. So it's always like kind of like as always in this course, you have to choose the degree. So I have to choose of a particular degree. So just to emphasize that, let me specify here of degree n. So you choose your favorite degree. Once you find the degree, then you find the polynomial that approximates up in that degree. So just to do a quick example, I'll show you how it looks on GeoGebra. So, but as an example, if the function had been, what if the function had been natural log of x squared plus x plus 2, okay? And let's say that I choose degree 4 because I already said what the Chebyshev points are there. So let's say n equals 4. So I said that for degree 4, the Chebyshev points were uh, they were -1, -1 over root of 2, 0, 1 over root of 2, 1. And so you would find the so you would find the Lagrange polynomial through those 5 points. So you find Lagrange polynomial through what? -1, f of -1, -1 over root of 2, f of -1 over root of 2, 0, f of 0, 1 over root of 2, f of 1 over root of 2, and then 1 f of 1. And of course, like here, because it involves natural log, you need to do some approximations. But if you kind of like do all of it, and do some after you do some simplifications and like, everything, then you will find that this polynomial will be, after simplifying, I just wanted to do something slightly higher degree so that you would see how it looks like on GeoGebra. Um, After simplifying, you will find negative 0.03 x to the 4 minus 0.13 x cubed uh, plus 0.38 x squared plus 0.48 times x plus 0.69. Okay. So just to wrap this up, let me show you how it looks like on GeoGebra. So let's see. So here, well, the purple curve is a function like natural log of x squared plus x plus 2. Um, I'm just graphing it from -1 to 1 because like the interpolation is just happening there. So that is the function for natural log. And those like the red points that you see here, they are the Chebyshev points of degree 4, for that degree or the Chebyshev nodes. So they're -1, -1 over root of 2, 0, 1 over root of 2, and 1. And here already you can see that they're like accumulating towards the edges, right? Because there's a more distance between these two than like the first ones. Then you have the corresponding points on the graph, right? And so the goal would be to find. So you kind of like forget in a sense about the function, right? So you have these 5 points, and now it becomes an exam one problem, right? Once you have those 5 points, you find the polynomial of degree 4 through those 5 points, and if you just plot the one that I wrote, you get this one. Okay, so that's how the polynomial looks like, and it's kind of like nice to. Let me use a different color. Let's say kind of like this darker color, and it's kind of like nice to compare it to the graph of like the natural log there. And then this is like the graph of natural log. I mean, the difference is very, very small, even already for like, 5 points. Like it's hard to tell them apart, actually. But like imagine, like, and this is kind of what we will start doing after the exam. Imagine if I had to try to integrate the function itself, how do you integrate natural log of x squared plus x plus 2? I have like actually, like, if I think about it, I have no idea. I wouldn't know what to do at the top of my head. I really wouldn't know how to integrate natural log of x squared plus x plus 2. I'm stuck. But how do you integrate the polynomial? Integrating the polynomial from -1 to 1 is the easiest thing you could do in the world. That requires no, like there's nothing to worry there about. So in a sense, you would expect like that is a good proxy, a good approximation for what the value for the integral for natural log would be. Um, and just imagine doing this where like if you had like 100 points in the interpolation or things like that. So like the idea is like with the polynomials, you can kind of like use them in many different ways to approximate quantities that you care about. And that uh, it's they're called quadratures. Like we'll talk about them after the exam on Monday. And so on Tuesday, we'll start talking about how do you actually approximate integrals. Once you know how to approximate integrals, you can approximate solutions of differential equations because to solve differential equations, you kind of have to integrate. So I'll tell you about that next week as well. But I think this is a good place to end. And if someone, again, I'll have like extra office hours on Monday before the exam. I'll finish posting some extra problems today. Once I have added them, I'll send you an announcement over Canvas. Also to post a mock exam. But if anyone wants to ask me something right now, also feel free to do so. I can answer that.